better. Full screen. Yeah, okay, we got audio and screen. Sorry about that. All right, we'll start again. Welcome to Ross.
All right, so I do polarized physics. So in talking about polarimetry, I want to talk first about why we want to polarize anything. So what measurements we can do with PIC, why we want to do them, and how we do them. And then once we have that done, now I can talk about how we create polarized beams, how we maintain them in the ring, and then how we measure the polarization. And I will tell you what these things mean. Okay. I give a slide not unlike this one a lot. In the 80s, we have the quark model, and we know that the proton is 2 ups and a down. And it seems very reasonable to say, okay, the spin should be carried by the quarks. And maybe if we get really lucky, it's the 2 ups will be 1 spin up and 1 spin down, and the down will carry the net spin. Sounds great. That's not how it goes. There's all this soup of quarks and gluons inside that, and the complex dynamics, all these things can contribute to the spin. So the spin of 1/2 is the net polarization of the quarks, sum across all the quark species, the net polarization of the gluons, and then some additional stuff that can come from angular motion. This is a plot showing, there you go. The integral of the gluon polarization over a range in delta x and over a range in delta x, smaller range in delta x. So what we did at RIC, which is the thing that just stopped running, the predecessor to EIC, is we discovered that the net gluon polarization at low x and at larger x is positive. So these things carry some of the spin of the proton. We asked this by doing longitudinal collisions, which is we collide protons back to back, or head to head, or back to back, or head to back, and we compare the rates of different final state observables as we do that. We can also ask, this is a longitudinal questions are, how do the partons inside polarize? If I collide like this, do I have the quarks pointed together or pointing apart? What they can make, what final states they can access, depends on how that lines up. We can also ask transverse questions about how the proton spin and the parton transverse momentum are correlated. All right. So that kind of sets up what we could do at the EIC. We can do polarized deep inelastic scattering. This accesses the structure function. Delta sigma, the polarization of the quarks, and delta G, the polarization of the gluons, going down from the Bjorkane X that we could reach at RIC down to much lower Bjorkane X. And I'm feeling like I dropped something off the slide because I definitely forgot to make those into nice, pretty symbols. And that's going to allow us, these are the plots here of the net quark polarization as a function of how far down we can go at X. And up here, where we already have measurements, we are pretty well constrained. We know the structure. And then as we go down to lower and lower X, the error bars blow up. And this blue teal error bars here is the state of the art from a long time ago. And as we go into the EIC projection, we get this much, much tighter constraint of what we can do. And the same thing for the gluons. Now, these don't tighten up as much because we don't access gluons directly at the EIC because gluons carry no charge. So the electron probe cannot directly interact with them, but we can get that through DGLAP evolution. If you don't know what that is, that's beyond the scope of this talk. Okay, so polarized GIS, that can access those things. We can also look at semi-inclusive deep inelastic scattering, where we have some selection on the final state, and that allows us to do some flavor-separated measurements of these net polarizations. So we can do the DU instead of just all the quarks, just the up quarks, or just the anti-up quarks, et cetera. And we also do transverse parton distribution functions, again, talking about how they line up with the orbital angular momentum. And then if we go to even more exclusive, we're just looking at really heavily specified final states, we can get into the things called generalized parton distributions. Because we hope to run more than just electron-proton scattering. If we can get some other beam species, we can also look at the neutron. And completely other thing, it's just a line here because I don't have the time to do it. We can also look at beyond the standard model physics. So other exotic things might be happening in parity violating scattering. Okay. The bread and butter of polarized physics is the asymmetry. This is a brand new slide for me because I swapped out what was previously a polarized proton over here for a polarized electron. So we take a polarized proton, longitudinally polarized, and a longitudinally polarized electron. That means they have helicity states. And we compare the cross-section of some final state observable we care about as a function of whether these things are aligned or anti-aligned. We take the difference over the sum, and that gives us this delta sigma, which is the polarized component of that cross-section, divided by sigma, which is the unpolarized component of that cross-section. And that cross-section has to do with just the sum over all the quarks we can strike, some sort of partonic quark electron interaction, and something about the polarization of that particular quark. So we can expand that sum into delta U times the charge squared of the U, delta D times the charge squared of the D, et cetera, as a function of Bjorkian X. And these deltas, they're literally just how much more frequent is it? Do we have a yeah? A close range hit.
Is there a stick up there?
Yeah. All right. So it literally is. We take the number of times that we see the quark aligned with the proton spin minus the number of times where we see them anti-aligned. It's just that difference. These can be large. And in just pure inclusive deep inelastic scattering, we don't have a way to pick out a certain quark. So all the quarks will contribute to the scattered electron data. However, we can use different targets, a proton, a deuteron. Oh, man, options. We can use different targets and different momentum transfer to tease apart which quarks are involved. And this is just, again, showing you for one particular species, the expected polarization as a function of X, and then going down here where we don't have as good constraints. Okay. To make an asymmetry, we need to know about the beam polarization. For spin 1/2 particles, we have two options. Either whatever we have inside there is polarized in the same direction as the beam or the opposite direction. I'm ditching the transverse for now, but this will work also for transverse if we are traveling along the beam spin up or spin down. Those are our only two choices. So we literally just have to count them. The polarization is defined to be the number of one spin direction minus the number in the other divided by the total number of things in the beam. And for spin 1/2, it's just 2 on the top, 2 on the bottom. We might also do some other beam species. For a deuteron, spin 1, there are 3 states. So we could in principle write PZ equals n plus minus n minus over the sum of all 3 possibilities, either spin up, in the plane, or down. But traditionally, and I don't really understand this, but it's a choice that was made, we normalize so that these 3 are normalized to 1. For spin 1, we have some options that we don't have for spin 1/2. For spin 1/2, P is all there is, and it's either positive or negative. That's it. If it's 0, there's just the same number of both species. But in spin 1, the vector polarization, the difference in positive minus negative can be positive or negative or 0. And that does not fully specify the situation because we also have the tensor polarization, which is saying basically just how are these 3 terms adding up to 1? Which one's carrying the most beam population? So if we actually want unpolarized, up here, we just need the vector polarization to be 0. But here, we need the 3 of them to be identically 1/3 of the total population of the beam. Okay, I had a picture up here, different slide. I'm not a theorist. If you want, I do have some slides. We can literally talk about this in terms of matrix amplitudes. I opted not to do that to you. here is our asymmetry as defined before. And that's the physics asymmetry. That's the, if I had this known spin state and I had this other known spin state, what difference would I get between the two cross sections? And I can, in principle, calculate that, or I can model it. But that's not what I can measure, because I cannot make a pure spin state and be 100% guaranteed that I only have that one spin state. Our beams will be mixed. They'll have polarization. And if I do a little bit of math shenanigans, I can write that the number in a particular state, and in my beam, the number spin up is 1/2 times the total number of the beam times 1 plus the polarization, or flip the signs to get the number of spin down. So when we actually look at what happens when we collide our two beams, if we know the polarization of this bunch and the polarization of this bunch, is that we'll get a cross section which is a mix of these nice clean cross sections. And I just basically did it out. So we have some fraction of the beams that are both spin up times the cross section for the double spin up, and then flip one of them, flip another one, flip them both, just sum and add, multiply and add, and then divide by the total population of one beam times the total population of the other beam. There's nothing magical there, but it is kind of nice that we can, well, I can rewrite this in terms of these polarization terms just by using the this definition. So I swap out the n plus for this and et cetera for all of them, and I spared you the math. But if I have a collision of two beams, one with my electron beam has a polarization PE, and my target beam, whether it's a proton or something else, PT, I can write it as this unpolarized cross section. The two terms instead of 4, because we're going to assume that if I flip both the spins, the cross section doesn't change by symmetry, by parity. So we have this unpolarized term here, and then we have a polarized term times the polarizations of both of them. Okay. Our goal here is to get back to this nice calculable or relatable to theory object. And we can't get there yet, but we could measure two different mixed states, this one and this one. And then we can form our measured experimental asymmetry as the cross-section of one minus the cross-section of the other over the sum. Same deal. And then we plug in this definition. We do a lot of cancellation. We discover that the experimental asymmetry that we measured is this nice clean one that we wanted times the polarization of each beam. So divide out, and this physics observable, this thing that we can relate back to the underlying theory, is all these measurables multiplied together. Difference over sum times 1 over the product of the polarizations. And the nice thing about an asymmetry is a lot of things that you need for the absolute cross section, like the total number of particles in the beam, these all drop out. And we can actually simplify this a great deal more. It's a sort of a counting experiment. I have, how many times did I observe the final state I like? Like my electron has a certain voxel and phase space, minus how many times did I see it in the other spin state over the sum. And this R is what's called the relative luminosity. It's admitting that we do need to know if we had as many of these collisions as of these collisions. And if not, we have to correct for it. Okay, but all the efficiencies of our detector tend to drop out. So it's just a counting experiment. Yeah. I dropped the relative luminosity here. So we're going to assume that this is a perfectly symmetric, same number in each. Do standard error propagation. I don't know if people read Bevington. Bevington 314, that's this equation. It's Gaussian error propagation. So I need some first derivatives. I got them over there. And the uncertainty on my asymmetry, I'm writing capital delta here just to avoid writing sigma everywhere, is 1 over the square of the two polarizations, the total population of the beam to the fourth, and then some products of these guys. I can make an approximation here that the asymmetry is probably pretty small. So the number of events that I count in a positive helicity collision and a negative helicity collision, it's probably about the same. It's probably about half the total number I see. I put this asterisk here because I did this to simplify the math, but you can actually do this thing out in its full glory without making this assumption. I said earlier, our atomic asymmetries could be large. Maybe the measured asymmetry is large, and we can get the same result. It's just a little bit more tedious. Counting experiment. So the variance on the count, the uncertainty on the counts is root n. The variance is n. That means that the uncertainty on our nice physics observable goes like 1 over polarization squared, and the total number of events. So if we want to do a nice high precision measurement, we need a couple things. We need to make this thing as small as possible, which means we need to make this number, this thing, as small as possible. We want to make this number as large as possible. We want intense, well-polarized beams. That's what we need at the EIC if we want to maximize the precision of these asymmetries. That's called the figure of merit. Okay. We talked about longitudinal asymmetries. I can also do a transverse asymmetry. So instead of polarizing my beams longitudinally, I have them transverse to their direction of travel. And now I just replace my positive and negative with left and right. And this is not handedness. This is literally whether the final product goes to the left or to the right in a frame that we can define based on the spin and the velocity vector of the particle that we're flipping. It's literally left versus right. And we can follow the same prescription where we talk about the fraction of the beam in each state. So this is the number that are transversely spin up in the one we're flipping and transversely spin down. We can make the mixture in the same way, and we can make our experimental measurement in the same way and relate it to the underlying a sub y, which is this physically pure version. And we're going to get the same thing, which is that our experimental measurement is just the polarization times the physics measurement that we want. Okay, that's what we want to measure. Now the challenge is to do the things that we just said we need to set up. So we need an electron beam, we need our proton beam, but we need these things to be polarized. So this is just I stole this cartoon. Here we have a train of bunches in the proton beam, and some of them are spinning positive helicity, some negative helicity, and they're changing every so often. And here's the electrons doing the same thing, some positive, some negative. We build these bunch trains so that any sort of time dependence in the efficiency of our detector, any changes in the behavior of the accelerator, they don't matter. We are doing positive helicity, negative helicity. We're flipping them to get every spin combination at really rapid fire. Or we can transversely polarize and do spin up, spin down. So we can do these kind of mixed collisions to get access to these more complicated physics observables. This is my menu of all the beams that we are going to talk about and or need and fingers crossed have at the EIC. So we have our bread and butter beam, the hydrogen ion, which is a proton. We're going to get bunch intensities up to 2e11. The goal is to get the polarization at the start up at 80% or higher. And this is to do that low X proton structure that I showed you on the previous pages. I'm going to talk about opus, which is how we get them. And the principle there is that we polarize electrons, because that's easy, and easier. And then we use a hyperfine transition to transfer that polarization to the nucleus. For helium, this is a helium-3, so it's a paired protons and one loose neutron. So that's a way to get a neutron along for the ride, since you can't accelerate a bare neutron. That gives us access to the neutron structure. And the trick is the same. We polarize an electron and find a way to get that polarization into that neutron. Deuteron, a little trickier. I'm actually not going to talk about the deuteron, but we have an atomic beam source, and then we use basically a Stern-Gerlach experiment. 1 second, which I'm not going to show you. Yes.
So why don't we have transversely polarized electrons here?
Why don't we have transversely polarized electrons? Or DIS, I mean, we could.
Has anyone ever studied transversely polarized electrons in DIS? That's experimentally
So
hard to do accelerator.
I think that, well, it's actually the transverse direction is the stable spin orbit version. Otherwise, they're going to precess in the magnetic field that is the same as this orbiting magnetic field. But the nice reason to do transversely polarized protons is because there's some structure. There's angular momentum. There's stuff in there. And electrons are point particles, or we think they are. You could probably do a lot of the same stuff if you made this one transversely polarized and this one longitudinally polarized, if you wanted to. Or do transverse, but then you wouldn't access that low X. That's an interesting question. All right. I thought you were going to ask, how do we get electrons? That's an easier question. We use a laser to polarize them. If you're noticing a theme here, it's really, we use polarized light to make polarized electrons, and then we either keep them or use them to make something else. All right, yes.
So the injection polarization is different, right? 80%, 90%. So this is the required polarization to do the physics, or this is the maximum we could do?
This is what we think these injectors can do.
Okay.
In this situation, polarization is a lossy process. Once we depolarize our beam, once we take some of the positive helicity here and flip them to negative helicity, we cannot preferentially flip them back. Okay, I thought someone was going to call me on that, but all right, well, there's a catch. We can polarize beams. I mean, we for practical reasons, we can't here, but in principle, beams self-polarize. And you can ask me about that later if you like. Okay, so we're going to start our journey here at the polarized ion source, OPUS, the optically pumped polarized ion source. And that plan again is we're going to take an electron spin that we get by pumping rubidium to polarize the rubidium electronic orbitals, and we're going to transfer it to hydrogen and into the nucleus from the electron state here. This is OPUS. We start with our atomic hydrogen injector, and these I'm just going to kind of run through the steps here. So we inject this beam. It's a hydrogen ion at a few keV. Then we neutralize it. So we use the fact that it was charged to get it up to a small starting run, and then we neutralize it. And the reason we have to neutralize it is we're about to put it into a really high field magnet. And to make it go in there without deviating to the side, because there's a lot of charge in here, is hard. It's easy if it's neutral, so it's just going to coast right in. So we make it, we neutralize it, we get it into our magnet, and then we have a helium cell there that we use to strip the electron we took right back off of it. And we're also going to slow it down so that it's going to interact with this rubidium cell at just the right speed to maximize that transfer of electrons off the rubidium onto our hydrogen atom ion. So it's going to pick up a polarized electron from the rubidium, and now it's neutral, and it's going to leave this cell without getting the big kick it's going to get from the space charge and from the magnetic field, so no E cross B effect. And then we are going to pass through this Stony transition region, which is a region where we carefully make the magnetic field go through zero so that the hyperfine transition flips the electron proton lowest energy state from the electron polarized to the proton polarized. So once we leave here, we actually have a polarized proton inside. And then we're going to pick up another electron to make a negatively charged ion. And then we can take that H minus with its shell of two electrons, one spin up, one spin down, so they can no longer take the spin back away from the nucleus. And we will send it off into the next stage of the accelerator with a protected nuclear spin. At 35 keV, so still a very sedate pace. And then, of course, it's going to go through this booster and through the AGS and up into the EIC. And how we take that polarization that we started with and keep it is a problem, which I'll tell you about in a little bit. All right, it's just kind of a tour here. The next one is how do we make our polarized neutron, by which I mean our polarized helium-3. This is hard and, well, they're all hard to do well. So this is a newer technology. The EBIS is not the name of the technology for the polarized helium, but it's the electron beam ion source. And this is how we can inject other ions other than protons into the ring. Same plan, which is to polarize the electrons and then transfer that polarization to the nucleus through the hyperfine transition. But this time we don't have rubidium. We actually get a pump directly on the electronic states of helium-3. All right, so here's EBIS. We have an electron gun, and we have an electron beam, a 10 amp beam that's just going along this short length, and then we decelerate it, capture some of that energy, and just do that forever. At the same time, it's going through these large magnetic fields as well. At the same time, we have a little chamber here inside that solenoid with a helium cell and a lot of little careful inlets to allow a small amount of helium gas, about 10 torr, into this cell. And then we're going to do the magic trick of metastable exchange optical pumping, MEOP, to take our neutral, our unpolarized helium-3 and make it into polarized helium-3. And then it's going to get squirted at very little puffs of this gas into the ultra high vacuum of this electron beam. And we do that with a membrane that it's got a very small opening. We open it for a very small amount of time and just adiabatically expands into there. And once these neutral helium atoms fall into this beam, we get electron-electron scattering that knocks the electrons right off of it. And now they get electrostatically trapped because there's this large negative charge in this straight line. So they don't leave this beam. They oscillate around it in a little gas. And they can't leave in this direction or this direction because although the electron gun has a decent kinetic energy, there's a small electrostatic bump here and here. So the helium ions just bounce back and forth inside this trap until we have a nice population of them. Then we flip the sign of the electric field here. They exit into our injector. They go into the ring, and then they are the ring's problem. Any questions? All right, I thought someone was going to say, well, how do you do that? Because here's how you do that. Can we... I'm trying to remember what state's underneath there. So we have a helium cell, and it's in the strong magnetic field of that solenoid. And what that does is it takes the various hyperfine states and it spreads them out. And it spreads them out enough that we can actually select and excite one of those hyperfine transitions without exciting all of them. So they're not spaced in a way where we have to put them all, or we have to move between all of them. So here's the deal. We take our ground state. This is the spin 1/2 of the nucleus. And this is the orbital angular momentum of the electronic orbitals. And this is the spin of the electronic orbitals. So this is our ground state. That should probably have been a 1 - 1. Sorry, no, this is not spin 1, spin 2. This is the total spin and then the spin projection. Okay. So the first thing we do is we put a little spark into this. And we do that to populate a triplet state that we can't get otherwise. So this is just, we spark the gas. There's some free electrons in there. They collide with the neutral gas, and they can bump them into arbitrary states. I'm particularly interested in this triplet state, where now we have 3 possible orientations of the electron spins, both up, a certain linear combination of up and down, both down. So now we can, through the hyperfine transition, these two states oscillate between each other just on their own. So if we have the triplet state spin up, it'll oscillate into triplet state spin 0 by transferring that spin to the nucleus. And fingers crossed, oh, I shouldn't say fingers crossed. Because the helium is 2 protons, that spin is primarily held by the neutron. So we are at a very high frequency, flipping between polarized electron states and polarized neutron state. So what we want to do is we want to capture this polarized neutron. At the same time, hyperfine mixing is also taking the state where it's spin down instead of spin up, and also mixing that. So this one is also oscillating between neutron spin up, neutron spin down at a very high rate. And that's where that strong field comes in. Because what we can do is we can take the state we like, this guy, and we can pump it up to a different state. So this is now, instead of being the 1s, now we have 1s 2p. So this is has an orbital angular momentum. There's also a state that takes the one we don't like, this down polarized neutron, and mixes it into a higher angular momentum state. But because of that strong field, we can pick a laser light that does this one, but cannot make this transition. All right. So what do we get? We move to this state where we have polarized our neutron. Then we pump it with our bright IR light to a higher orbital angular momentum state. And then this can decay from whatever nuclear state with this orbital angular momentum back down to the ground state by emitting a photon. So in particular, the state that we like, we can drop that back off. And if we manage to excite this other one, which we can't because we can't do this step, we would also be making the same state with the neutron spin down. So the result here is that we can access this state only in the neutron spin up. And then through metastability exchange, which is the fact that, or the principle, which surprises me, but it is what it is, that if you have 2 helium atoms, and this one has an excited state electron orbital system, and this has a ground state, when they collide, they flip who has the excited state. So now we have created our polarized helium in its ground state. Okay, so we are essentially slowly pumping this. And once it is in this ground state again, we have the same protection that we had before. Because there is a singlet instead of a triplet state for the electronic spins, we can't do this hyperfine transition. So we can't lose the neutron spin. So over time, we slowly accumulate. And over time, I mean like over hours, we can accumulate this net polarization. And then once we have it, you warned me this was getting weak. Oops, I cannot go back, can I? All right, well, once we have it, then we can do that injection. Yeah.
It works again since you click
Oh,
on the screen.
yeah, you said someone was telling me that shaking it was helping out.
You want to go back or?
I don't really need to go back. But yeah, so once we have that polarized helium with its protective shell, we get it into this beam, we knock both of the electrons off at the same time, and it's now just a bare polarized helium-3, makes its way into the accelerator. Okay. One more. We have now 2 species. We have the helium-3 and we have the protons. We polarize them. We've injected them into the hadron ring. We need to make electrons. And same deal, use a strong laser to circularly polarize our electrons. But now that's basically all we need to do. It's harder than that, but it's all going to happen in this electron gun, which will be over here at this other accelerating stage. This picture is actually taken in the basement of this building. I don't think they'll let us in there, but it's been developed here, even though it's being developed by Brookhaven folks. All right, how does that go? So here's that metal orb that you saw, and most of the magic is happening in the gallium arsenide photocathode. So we take the bound states in our photocathode, we shine a bright circularly polarized light on them through some magic tricks. We only excite one spin state into the conduction band, and that, again, through the way that gallium arsenide photocathode is made, these polarized electrons drift out of the bulk of this to the surface and emit freely into the vacuum, after which we just have to electrostatically accelerate it from the cathode here, which is at high voltage, towards the anode, and it makes a beam that we can send into the electron linac. I think this is really neat. This cathode is really, if you're condensed matter folks, you can probably make more of this than I can, but we have a really complex structure. So we have a wafer underneath, and then we have some gallium arsenide to flatten that out. And now we're going to start building towards this green block that we want by slowly doping gallium arsenide phosphorus a little bit more, a little bit more, a little bit more to change the spacing to match our cavity here. And I say cavity because this forms a Fabry-Perot cavity for the laser light. It has a structured surface here that is a Bragg reflector for the frequency of the light. And then we have a spacing that matches the wavelength of the light. And then a superlattice here. This is the material that is carefully engineered to split its valence structure, its conduction valence structure enough that our light will excite only one spin state of the electrons. And then the top of this is a cap to strongly encourage those electrons to leave. So we have a very highly p doped, so there's a lot of electron holes here to encourage the electrons to drift upward. And then we put cesium or something else on top that has a literal negative electron affinity. Once the electrons get here, the cost to jump off the material and into the vacuum is negative. So they just spontaneously diffuse upward and then jump off. And they're in a really highly polarized, I think it's like 90% polarization state. Okay. Whew. And we put them into the linac, which I'm not going to talk very much about. And we accelerate them, we collide them, we make our physics. Before I jump to the next question, which is how do we get these beams up to the energies we care about, and how do we keep them polarized? Are there any questions about the injectors, the sources? I think they're really neat. Okay. If we want to collide particles, first and foremost, they need to stay in a closed orbit. I think someone else later is going to talk about beam accelerator physics. So,
Yeah, we had Christoph last week. I think there's a little more end of the week.
okay. So our beam is not this monoenergetic perfect line that's going around in a circle. We have some emittance, which is to say there's some transverse motion, and we have to keep focusing it in. The bread and butter of that is the focus, drift, defocus, drift lattice. So here's the beam envelope as it's going through these essential lenses. Because these are magnetic lenses, we can only focus in one direction at a time. So we have to kind of keep doing it. So we focus one, then we defocus it and focus the other. Then we focus one again, defocus it, focus the other, and do that to keep the beam inside that envelope. And if we do it right, then that kind of photo thing is happening as we go around. And then from time to time, we'll have an accelerating cavity that will add some momentum, and we'll just keep going around and around. Great. If it's perfect, we're done. But let's imagine we have a small defect. The field here isn't quite right. Then what we want is to avoid any sort of beat pattern with that defect. We don't want an electron that's in this bunch, sorry, or a particle in this bunch to always be at the same point in phase space when it gets there. It's going to get some sort of kick we don't like. And if it adds up that kick every time it's getting there, then it's going to rapidly fall out of the beam. And in fact, that's a very, very rapid way to lose the beam. That's how we lose the beam. So beam particles should not be in the same transverse position each time they pass the defect, nor every nth time. We don't want to do it every second time or every third time. And also, and I think the beam folks will get into this a little bit more, some of the other magnets that are in this will mix the up-down oscillation into left-right oscillation. So we don't want there to be any beat patterns in how frequently we are oscillating vertically and how frequently we are oscillating horizontally. So this is the integer structure we want to avoid, where Qx is called the horizontal tune and Qz the vertical tune. That's how many oscillations we make in one lap around. So if this is if the vertical tune is 1, it means that if we started at a certain point in phase space here, by the time we get all the way back around, we're at the same point in phase space. We want to avoid that. And if we look up to third order, we want to avoid all of these straight lines. These plots are showing the beam tunes from one integer to the next. And the reason I'm only doing that is because I don't care if it's 30 oscillations plus a tenth, or 3,000 oscillations plus a tenth, or just a tenth of an oscillation. It's only that non-integer part that's going to be helping me. Any integer is a bad integer. So we only care between one integer and the next. And because our beam is not monoenergetic, it's got some spread to it. We're not at a point in this vertical tune versus horizontal tune world. We're in some sort of small area of it. If I go up to infinite order, these lines, which represent the bad resonances that we want to avoid, will eventually fill all space. So we can't avoid them forever. And in fact, we can't get a piece here that has a finite size and avoid them for very long at all, because our beam has some spread to it. But we can find a spot that avoids as many of the low order, which is the more powerful resonances, as we can. So we pick a working point that's well off of an integer, and it's off of those diagonal and 1 to 2 and 1 to 3 diagonal lines. Okay. Oops. Polarized beams have their own version of that problem. So in addition to the vertical and horizontal tune, we also have to think about the spin precession as we go around. Is that a question, or is that just we good? Okay. We also have to talk about how much this spin is precessing as we go around. If there's no anomalous magnetic moment, then the precession in a ring of the beam is exactly the same as the orbital period of the beam. So it would not accumulate any rotation. But there are anomalous magnetic moments, and so we get a small additional precession. If we have this thing transversely polarized, it's going to wobble as it comes around. And we have our equivalent of the resonances to avoid. We want this, our spin tune is the Q sub S, which is the gamma factor of the beam times the magnetic moment, written in funny terms, but don't worry about that. So if there's an imperfection, then if our spin tune is an integer, then we'll keep hitting that imperfection at the same point every time, and it's going to rapidly depolarize our beam. But even if we don't have field imperfections like that, the structure of this and the fact that the orbit is not a straight line, it's not a fixed line through the dead center of all these magnets, means that even if we built it right, there will be these intrinsic depolarizing resonances where the spin tune is some integer multiple of the periodicity of the ring times the vertical tune. And the periodicity of the ring is this, but for practical reasons, we don't build a ring that is unique the whole way around. We take some sort of super lattice of photo stuff and we repeat it all the way around the ring. So if I go around this ring, I see I've got bending magnet, focusing magnet, bending magnet 4 times. So this ring has a periodicity of 4. And we would like to avoid any resonances that have that structure. But there is a catch. Oh, nope. There is a catch which is missing from my slide. We can't avoid them. If we're accelerating, if our vertical tune is a number, and this is a number, and we want to make our beam faster and faster, gamma is smoothly going through all values. It's going to hit every depolarizing resonance. Thus, there is no way to make polarized beams. Unless we had some clever trick. A Siberian snake is a magnet where the dipole precesses around it. And what it does is it takes the electron, the beam on an excursion where it leaves the center line. And as it's moving through this magnet, it flips the spin from spin up to spin down. And the really simple version of this, okay, there's a Siberian snake, is we're going to naturally accumulate some depolarization. We're going to move our polarization vector off from where we want on one pass through this. And then on the next pass, we're going to flip it upside down, and it's going to precess backwards. So it's going to experience all the same depolarizing resonances with the minus sign. So if it goes around twice, it's back where it started. Great. That's not really how it works. Unfortunately, this Siberian snake only fixes it in one dimension. So if we really want to do it, we actually need a pair. We need to have a Siberian snake once that rotates it around the beam direction, and once that rotates it around the transverse direction. And in principle, that's all we need. However, at high energy, the resonances get so severe that we can't just live with one pair of spin it once, spin it again. We actually need to have a bunch of these. So at the EIC, if we do this, one rotating it horizontally, one rotating it vertically, the spin tune ends up being proportional to the angle between those two rotation vectors, which means it just becomes 1/2. If we pick a longitudinal and a transverse, no matter what our G factor is, so no matter what G is, no matter what gamma is, it doesn't enter into it anymore in that perfect world. Okay. This is what the spin resonances look like at RIC. We got some Siberian snakes here and here. And as we go up in the energy, as a function of gamma, these are the strengths of those resonances. We have to go through them. But we can turn on and off the snakes. RIC didn't have enough snakes all the way along the injection to just have that spin lock that tune lock at 1/2. So on its way up, we could turn on or off partial snakes to avoid these resonances. Really? Okay. For completion's sake, electrons are a different beast. In the ring itself, we are not accelerating them. They're already at flat top in there. So they don't have to go through any depolarizing resonances in the ring. All we have to do is make sure that the spin and the vertical tunes do not add up to disaster. And so we do that. The problem with electrons is that every time we bend them, they emit a bunch of synchrotron light, proportional to the 4th power of the energy. We cannot use Siberian snakes to fix this because it's not deterministic. We can't flip it around so it randomly emits the same photon in another direction. And our only option here is to re-inject bunches periodically. All the bunches are going to slowly depolarize over time, and then we dump them one by one and refill them. Does anybody know, is there another way to polarize? Is that something else we can do in an electron ring? In principle, the Sokolov-Chernoff effect does give you a slight preference in the emission of synchrotron light that tends to polarize it over time. And that is an effect that's happening here, but it's over an extremely long time scale. So we have to do this. Okay. EIC, we have 3 pairs of Siberian snakes. And to my current understanding, each Siberian snake actually does two rotations, so that there's a lot more effective pairs of them, and they are placed one on each straight segment of this hexagon. This is a list of the number of resonances we have to pass through as a function of species, and the maximum of G gamma, which I guess I forgot to fill in for the electron. Okay. We produce these beams at a high polarization. Our intention is that once again to the EIC ring, they stay well polarized for a good long time. We are, by definition, we want to measure their polarization all the way through from the injector up to their storage in the ring. So we have polarimeters in the ring that can operate across the whole spectrum of energies. We have polarimeters in the booster stages to track the evolution of that polarization. And then we have polarimeters around the interaction region to measure the spin vectors right before we collide them. All right. These are our defined conditions. We've got to measure the proton and the electron across their whole energy range. The stores are going to be long, so these measurements need to not be too destructive. If you saw the bunch trains earlier, to avoid some systematics, we are flipping spins essentially on a per bunch basis. So any polarimeters must be able to resolve individual bunches. It doesn't help us to get an average polarization, which will be 0 over any large stretch of this. And the bunch spacing is really, really fast, 10 nanoseconds between them. We'd like to measure the absolute beam polarization. It's better than 1%. Earlier, I showed you the figure of merit that says the polarization has to be high. Because the polarizations both enter multiplicatively, if they have a large uncertainty, they ruin your measurement, even if they're really high numbers. We want to track the evolution of the polarization over time in the beam, so these measurements have to be pretty fast, bunch by bunch polarization. We'd also like to know the profile of the polarization. These beams are not, dots. They've got a transverse spread. And it might be that the core and the fringe are polarized differently. We certainly experience a different amount of depolarizing effects. So we'd like to track that so that when we talk about the average spin or the average polarization of a bunch, we're not just looking at one spot in it and assuming it's flat. And then we want to measure the polarization vector of the experiment. Okay. All right. So how do we build a polarimeter? I've got two kinds of beams I can think about. I've got my transversely polarized beam A. I've got my longitudinally polarized beam B. I've got a box. I got to put something in here. So what are we doing? This is an actual question. Can I see by show of hands whether we like transverse or longitudinal? Who says transverse? Who says a little bit transverse? Longitudinal? Nobody? What can we do on a bunch by bunch basis to look at the polarization? Sure.
Molar scattering.
Molar scattering. Why?
Can't that be more or less precisely calculated?
Ambient has a spin dependent term. We want a cross section that we know has some spin dependence. And once we know what sort of cross section we like, we know what we want to build. We could, in principle, stop this beam in a thick target, but because we want to be non-destructive, we won't do that. However, we cannot measure the polarization without at least affecting the particles in the beam that we interact with. So non-destructive doesn't mean you can't touch them at all. It just means don't take too many of them at once. Okay. Right, let's talk about A. Good answer. We need a spin-dependent term, and I'm going to go with Mott scattering. Mott scattering is electron scattering off of a nucleus, and there is a spin-orbit coupling if your electron is polarized, which means that for a polarized Mott scattering, you have the unpolarized Mott term times this correction factor. And this correction factor has the polarization vector of the electron times the normal vector. And by normal, I don't mean normal to the plane of motion of this electron, which has a transverse spin and a longitudinal direction that's going in some big loop. It's not that plane. It's the interaction plane, which can be rotated from that plane by an angle phi. And now we have theta and phi dependence here. If we set phi to 0, that's going to the left. If we set phi to 180, it's going to the right. So there'd be a difference or asymmetry, if you will, between stuff going to the left and stuff going to the right. Stop me if this sounds familiar. Okay, so it's a counting experiment, just like it was earlier for our physics observables. We're going to count how many go to the left and how many go to the right, and we can calculate what that should be from the polarized Mach cross-section. And then we just do our asymmetry, the difference between left and right divided by the sum. And we throw that into our known calculable cross-section. We get all this stuff, and all of these terms cancel out. So all the sigma mod 0, the unpolarized Mach cross-section, cancels out. And this is, again, why we like asymmetries also for physics measurements, because I don't need to know the acceptance, this kinematic factor that tells me about how likely I am to hit this, as long as I make the two the same. All right, so all we need, the asymmetry we measure in our detector, left-right asymmetry, is going to be directly proportional to this S function, which is called the Sherman function, times the polarization of the beam. Comes right out. So we just need S. Here are the Sherman functions. This is the S as a function of beam energy, and this is S as a function of scattering angle. All right. So what did I do wrong? I drew my detector here. What's wrong with the detector? When in doubt, use process of elimination. There's not much there. I probably should have put this on. Pop out for a second. The asymmetry measure is the Sherman function times the polarization. So if we have a high polarization, we'd like to see an asymmetry. So what do we have to do to see an asymmetry here? Where do we have to be on the Sherman function? Say again? Away from 0. We don't want to be over here. There's no analyzing power. There's no difference between spin up and spin down if we're over here. So I want my scattering angle to be like 150 degrees. Those shouldn't be there. They should be here, backscattering. Yeah. And this the Sherman function here is what's generically called the analyzing power. The analyzing power, A sub y, is the maximum size of the asymmetry we would get. The size of the asymmetry we would see in a perfectly polarized case. So if A sub y is 0, we have no sensitivity and our polar emitter doesn't work. All right. We built these. We have 2 Mott polar emitters. Yeah, I couldn't find a better picture of this, but this is our electron source. Beam can be bent and put into this polar emitter, and you can see the beam is going in this direction, and the detectors are backwards. And they're backwards because that's where the analyzing power is bigger. This is a gold foil, so it's probably pretty destructive to the beam. We're going to use it to calibrate the electron beam polarization, but we're not going to run every electron through it. There's actually 2 of these at the injector. There's one at 20 keV right after it comes out of the gun, and then at 300 keV once it's gone a little bit further down. So it comes down this way and then goes to a larger one. Detectors are bigger and still backscattering because that's where the analyzing power is. Okay, we could have chosen B. So if you in your head secretly thought, I thought B was right and I feel bad, you could have done that. Really? I thought I was going to make you guess on this one again. All right. We can have Compton scattering. This is electron-photon scattering. And the Klein-Nishina formula is unpolarized, but there's a correction term. Stop me if this sounds familiar. Unpolarized times correction term. And this correction term has the polarization of the electron, the polarization of the photon, and this analyzing power, which is a function of the energy of the photon. How do we measure this? We can't do left-right anymore. There's not a left-right asymmetry here. This has to do with the polarization. So we can't flip this one. We want to measure that, but we can flip this one. So every time this particular bunch comes around, we'll shine a different polarization of light on it. And we won't do left-right, but we'll do A-B comparison depending on which light we're shining at the time. So our photon comes in, strikes our electron, backscatters to about 180 degrees. And that's where we maximize that. I say that on the next slide. All right, so we flip our laser helicity. I mean, again, it's a counting experiment. Now it's not left-right. We do have to do this over time, but these beams are going very fast. We're going to get a chance at this particular bunch of electrons a lot. The positive helicity, some kinematic factors, the unpolarized Klein-Nishina as a function of photon energy, and then the correction for polarization. And then when we flip the helicity, we just get a minus sign in front of the photon polarization. Do the same asymmetry as before. And what we will measure is polarization of the electron times polarization of the photon times the analyzing power at whichever energies we have for our photon. This is QED. This is analytic. We can calculate this. I do not calculate this for you. But backscattering gives us the largest photon energy, where rho is the ratio of the energy the photon has to the maximum photon it has. Here you can see the A sub long, but this is the analyzing power as a function of rho. You see that it grows as we go up to higher photon energy. And this is done for 3 different beam energies. So as we go up to higher energy, the analyzing power actually gets bigger, which is nice because we want this thing not to peter out at the top energy of our accelerator. Schematically, our electron beam comes in, we shine our laser as close to head-on as we can, and we look for it to scatter right back along the electron direction. Conveniently, since electrons are charged and they're going in a loop in the ring, we will bend them out of the way sooner or later, and then right downstream at 180 degrees, we can put our photon detector. So it's a counting experiment. It's true that some of these electrons, if they do have this hard scatter, they will lose some energy. They won't get the right energy to stay in the beam anymore, and they too will drop out. So they'll bend too far in the bending magnet. And we can also pick them up in an electron detector. But wait, it turns out there's also a transverse analyzing power. As a function of how far vertically up or down you are, you can measure the transverse and the longitudinal polarization of the beam at the same time. So if we really did it carefully, we have this longitudinal term, which is what we just talked about, and we have this transverse term. So what do? We put detectors there. If we take the region where the electrons fall out of the beam and we segment it finely so we can see how many go up versus down, we can also simultaneously measure the transverse polarization. And together, that gives us the whole vector polarization of like, what is the axis along which our beam is polarized up or down. Since in our interaction region, we generally, or we're at least sometimes interested in longitudinally polarized particles, but the stable orbit for particles is transverse. We don't want them in the plane. We have to rotate them from vertical to horizontal on their way in and then back to vertical on their way out. So it's really handy to be able to measure how well we're doing that right before the experiment. So that's the Compton polarimeter. This is IP6. That's where EPIC is going to be. And right in front of it, we'll measure bunch by bunch the electron vector polarization. This folks at JLab are working on this. I wanted to say something because they're doing a lot of work, but I admit it's not my area. They're building a nice laser based on a laser that they have for their polarimeter in Hall C. And although I've made this experiment, this polarimeter, look fairly straightforward. And I apologize, I do that throughout. I'm an optimist. But at the same time that these nice asymmetries are showing up, there's also beam background, which might be bunch by bunch stuff that's going to mess up these asymmetries. And this stuff that's out of time, that's showing up in your detector and you don't know what to do with. So there's a lot of noise. And we have to separate the signal from that stuff, avoid other backgrounds. And so the detector has to be built more carefully with better timing and a better understanding of how it deals with those. And they have a tungsten converter in front of these small diamond strips to get that where the photon is, as well as where the electron is. Okay. I'm not going to, I think I might play that game one more time with you where I ask you to build a detector. Hadrons are tougher. And the challenge is that for the electrons, we can actually compute these asymmetries. But when we try to do it for the hadrons, we have to go into QCD, and that just is not going to help us. I'm realizing, how am I on time here?
We can flex a bit.
All right, I'm gonna speed it up. Okay, but we can work in the Coulomb nuclear interference region, and the advantage here is it's mixing Coulomb, which we can understand, and nuclear, which we are going to have a hard time with, in a place where we can calculate it. And we're going to get a interference term that has a spin flip. And we get a little bit of analyzing power, like 4%. So if you have a 100% polarized beam, you'll see a 4% asymmetry. But we have to calibrate it somehow. We don't have the absolutes. There's two ways we're going to use this. We're going to talk about a hydrogen jet where we do protons colliding with protons. We'll do a proton carbon scattering as well. And for any of these experiments, it's hadrons on hadrons. So we can think about it as the analyzing power of the beam times the polarization of the beam. Oh, sorry, the asymmetry in the beam is the analyzing power of the beam times the polarization of the beam, or the asymmetry that we see from the target, if we're flipping the spin of the target, which we're going to need to do, is the analyzing power of the target times the polarization of the target. So we can actually measure either one of them, treat it whichever way we like, but we need to know this A sub n. All right, for hydrogen jets, because we have identical particles, the analyzing power, you notice that the apostrophe here is missing. That's not an accident. Because they're identical, the analyzing powers are mathematically required to be the same. And if that's the case, you take these two terms, the asymmetry that we see if we're considering spin flips in the beam, and the asymmetry spin flips in the gas jet of protons that we're colliding, and we can form a ratio and get rid of these unknown analyzing powers so that the polarization of the beam can be related to the asymmetries we measure. The beam the asymmetry as a function of flipping the beam, and the asymmetry as a function of flipping the jet polarization. And if we measure the polarization of the jet separately, we know the polarization of the beam without getting into QCD. For a gas jet that's not stuck in a collider where we are allowed to take as much of it as we like, we can do that without trouble. Here's what it looks like. In the interest of time, I won't go into too much of it here, but the gas just squirts down into the vacuum, and we have detectors around the interaction region because the I have it. Okay. There's only a certain kinematic region, basically ultra low Q squared, where that collision works. There you go. Gas jet particle hits it, and at 90 degrees in the center of mass frame is about where we have the analyzing power to see these polarizations. So this is what was built more or less at RIC and in operation, and we intend to bring it over to the EIC. I won't sweat the details. Just neat. Because we want to scatter slightly forward in both directions, we can do this for both beams simultaneously. And just look at, sometimes both beams are there, sometimes it's only one, and we get a very clean measurement of that. Sometimes it's only the other one, but it's in the same vacuum. At the EIC, life gets harder. Here's RIC with 120 bunches, 100 nanosecond spacing, short length. Here's the EIC, 10 times more bunches, 1/10 the spacing, which makes sense, and 1/10 the length of each bunch. So here, this is the kinetic energy of the recoil and the time that arrives at our detector. This is great. This is for one bunch. At the EIC, these all overlap. So we can't use just the time of arrival anymore to tell us about that, which bunch we're probing. So we have to be more careful here. And I'm going to skip the carbon fiber polarimeter, except where the gas jet is really, really wide, the carbon fiber is a thin line. And we're going to do the same trick. We're going to use the same Coulomb nuclear interference, but we don't have an absolute calibration. So we use the gas jet to calibrate it to figure out what asymmetry this device sees for a certain polarization of the beam. Once we know that, we can use this to scan not the whole beam, not the beam integrated over the whole thing, but narrow slices of it. So we can see the profile of the polarization and the intensity. And that allows us to look at this parameter R, which is the ratio of the width of the Gaussian for the beam and the width of the polarization. Same thing. They may not be evolving at the same time. All right. At the EIC, you dump a lot more energy into this fiber. And also because the beams are more intense, it deflects towards them. So knowing where we are in the beam gets more complicated. There's more wake fields. It's going to be hard. Okay. So we talked about why we care. I want to learn about the spin composition of the proton. And then at the EIC, I'd love to know about the neutron. EIC, we want everything: higher intensity, higher polarization, and more precise measurement of polarization. We have the tools to make these beams. Prototypes are better, exist for all of the polarized sources. We have the techniques to accelerate and preserve the beams. That's the Siberian snakes. We have to expand on these. We need more snakes in EIC than we needed at RIC. And we have the electron-proton analyzing power, which is getting there. And these are our various sources. I'm going to leave it there and open any questions you might have.
Thank you. Questions?
Could you describe, you said that the beams will self-polarize. Could you talk about the mechanism behind that?
That's the Sokolov turn-off effect. And that is a preferential emission of synchrotron light with for electron. It's a preferential emission of synchrotron light with one polarization, which will spin flip the particle that emits it. And that preferentially will polarize with respect to the bending magnetic field. So the problem is that goes with some power of the mass. So although that's maybe practical for electrons in some settings, it's not practical for our ions. It's also, in this setting, doesn't evolve fast enough. It doesn't relax into that state fast enough for our tastes, because the half-life, what's the right word? The time constant of that is tens of hours, where we're only expecting to hold for 8 hours.
What's the effect?
Sokolov turn-off. Okay. Sokolov turn-off. Well, other questions? Yeah.
Okay. So we have the options of mod scattering, complex scattering for the electron polarimetry.
We also have molar scattering.
So
it's also in there.
choose mod and complex scattering.
I chose mod because it's easy. We choose molar as well, but we don't want to choose molar in the ring because it's far more disruptive. We have to find a way to get electrons in there. And one way to get electrons in there is to put a foil in the beam.
Right.
But that's not practical. In the injector, however, I think we are going to end up putting a molar polarimeter in. Okay. Yeah.
So at least one way at class that we try and get a handle on the beam and target polarization is looking at elastic scattering from electron and nucleon. Is that something that's been considered for the EIC?
electron-nucleon elastic scattering.
Because you can use the form factors to constrain the asymmetry, which are known relatively precisely. At least
That's a good
relative to
point.
DIS.
Yeah. I honestly don't know, but that's a good point.
I mean,
I mean,
the cross section is going to be pretty small.
in the deeply limiting case, that is what the Mott polarimeter is doing, but you could presumably do that harder. You're gonna. I'm intrigued. I mean, I guess in principle, a gas jet couldn't hurt the electron beam any more than it hurts the ion beams. So the idea that you could do that slowly, maybe, I don't know.
Oh, I mean, like literally using your collision data for that.
Oh, using the collision data.
And then sort of taking the average over a period of time.
I don't know for sure, but that sounds like a very good idea. There might be some obvious reason that we can't do that, but I think you could do that.
I mean, it can set the overall normalization.
Thank Ross again, so